Week 3 AP Stat Need to Knows. Alright. So the first question wants us to describe a distribution and know the resistant and non-resistant measures of center and spread. So it says that we need to sketch a uniform distribution. Alright. So for a uniform distribution, essentially for all your given x values or for whatever you input, they all have a similar frequency or all have a similar y value. Alright. So this is what that representation will look like. Okay. So what's the relationship between the mean and the median? All right. So because they all have similar y values, guys, all right, your mean and median is equal to each other. All right. So again, for a uniform, the mean and the median and the mode will be equal to each other. Okay. So which measure of center and spread should be used? Okay. For center, the best representation is your mean, all right, or your median, okay? Because they're both equal to each other, either one could be used interchangeably based on what's given in your question, all right? The best measure for spread, all right, will be your range, okay? So that would be the best measure for spread in this scenario, all right? Or at times, okay, standard deviation, all right? But it's less likely that you'll use your standard deviation. It's more likely you'll use your range, all right? So now we're going to do our next question. So we need to transform data. So we're going to use operations that affect mean and standard deviation. So for the information listed above, what is the mean and standard deviation of this scenario right here? So for the mean, all I'm going to do, guys, is just replace the value for the mean for C, which would be 125, put that over 4, and add that with the mean value for D, which is 30, and put that over 5, because that's what this equation says, C over 4 plus D over 5. So we know that 125 divided by 4 is 31.25, and you should know mathematically that 30 divided by 5 is 6, okay? When you add those together, you get 37.25, and that would be the mean for that scenario. So now we're going to find our standard deviation, okay? When we're trying to find our standard deviation, guys, we're basically going to try to find variance and take the square root of variance, all right? So to calculate variance, I would be doing the standard deviation for C, which is 25, divided by 4, then square it, and then add that to the standard deviation for D, which was 6, divided by 5, and then square it. So to get standard, so this is how you calculate variance. To calculate standard deviation, you have to take the square root of variance, okay? So when I calculate all of this, guys, I would get 6.36. Okay. So let's try the next one. So the next one says, what is the mean and standard deviation for 5C? So all I'm going to do here, guys, is just substitute the value for C, all right, into each of these equations. Okay. So for the mean, I would just do 5 multiplied by the standard deviation for C, which are the mean for C, sorry, which was 125. And then that would give me 625, all right? And then for standard deviation, because we're not adding it to anything or anything like that, guys, all I have to do is just substitute that value, all right? So I would have 5 multiplied by the standard deviation for C, so 5 times 25, which is 125, okay? So the next one, so again, we're again trying to calculate the mean and standard deviation, all right? So for the mean for this one, guys, I'll go ahead and substitute it for C and D. So I'd have 2 multiplied by C. C is standard deviation for, or the mean for C was 125, and then add that to the mean for D, which was 30, okay? So when I calculate that, 2 times 125 is 250. 250 plus 30 is 280, okay? So now I'm going to calculate the standard deviation, all right? So when I'm calculating the standard deviation in this case, guys, all right, I'm going to essentially calculate the variance and then take the square root of it, okay? So to calculate variance of 2C, I would do 2 multiplied by the standard deviation for C, which was 25, and then square all of that. And then add that to the standard deviation for D, because there's no coefficient being multiplied. I just use the standard deviation for D, which was 6, and then square that, and I take the square root of all of that. So underneath is the variance, the square root of variance is standard deviation. So when you plug in all that into your calculator, you'll get 50.359. All right. So let's try the next one. So the next one says we need to interpret residual values using the linear regression equation to describe a residual given the data point. So the Minitab output below is a least squared regression line, LSRL, analysis that is used to predict a student's exam score percentage based on the number of hours studied. Alright, so they're not geniuses like you. They actually have to study to get a better score. Alright, so we need to first define the variables. So what's the explanatory variable? Well, the explanatory variable is what your experiment or your analysis is based upon. Alright, it's what you're going to use as your x value to calculate the responding value or the y value. Alright, so it says it's based upon the number of hours studied. Alright, so of hours studied. Because essentially, if they studied more, they should get a better score, right? So the response, or what's going to respond to the amount of hours studied, will be the exam score, all right, as a percentage. So the exam score as a percentage, all right? So it says, what is the equation of the LSRL given the stat output? So the LSRL is what we use to represent our linear regression line or our least squared regression line, okay? So anytime you think about the word line, you need to think about the general form for a line in slope-intercept, which is y equal mx plus b, all right? Where m is the slope and b is the constant, all right? In this case, because we're trying to find the LSRL equation, we're going to actually use the predicted value for y, which is represented by y hat, all right? And then we're going to represent it as b being the constant plus ax, all right? So in this case, we're going to have y, or y hat, is equal to the coefficient for the constant was 50, and then the coefficient for the hours, which is essentially changing over some period of time, all right? You'll be getting 4.5 increase every single time that you would do some type of studying, okay? So this is where we add our x attached, all right? So what we're going to do now is that we're going to identify and interpret the residual for a student who studied for 10 hours and scored a 92 on the exam. So this 10 hours is the amount that they studied for. This is what they actually got on the test, okay? So this is their actual score. What we're going to do is that we're going to use our predicted equation to see, really and truly, if they studied 10 hours, what score would we predict for them to get? Are they going to get the 92? Are they going to get more or less? Okay, so we're going to try to use a prediction to see if the prediction was actually sound. So we're going to replace the x value in this equation with 10, all right? We're going to have 50. 4.5 times 10, anything times 10, you either move the decimal point once to the right or you add a 0. In this case, we move it once to the right, it becomes 45. 50 plus 45 is 95. So they actually got 92, and we predicted they should have gotten 95. So we predicted more than what they actually got. So because we predicted more, we can say we over-predicted, all right? So it says that we need to identify the residual. So we need to first calculate what residual is. So to calculate residual, all right, so to calculate residual, you do actual, which is your y value, minus your predicted value for y, all right? So I would be doing 92 minus 95, which would be -3, all right? So that's what the residual value would be. So let's write what we interpret from this scenario, okay? So the interpretation would be based on our LSRL analysis, the residual value was -3, which means our model tends to overpredict, all right, tends to overpredict for exam score based on number of hours studied. Okay, so I wish we had a little bit more space in that area. So Again, just like that. Okay, so based on our LSRL analysis, the residual value was -3, which means our model tends to overpredict. That's what this word is, overpredict. So our model tends to overpredict for exam scores based on number of hours studied. Okay, so let's try the next one. So the next one, we're trying to identify types of biases and experimental designs. So it says explain the difference between sampling bias and non-response bias. So sampling bias is essentially stating that when you take that sample, it's only looking at a specific group and not giving you a holistic view of what your entire data is using to represent. All right. For example, if I ask students, is Mr. Sorensen a good teacher? If I only ask students who have gotten level 5s and level 4s with me, yes, they're definitely going to say I'm a good teacher because I was able to get them to be a level 4 or level 5. All right. However, if you ask students who got level 1s and 2s with me only, they're going to give you a completely different response, all right? Because when you looked at that sample, you're only picking people that were already given a certain bias based on who they were, all right? So essentially, it's when, or to have a formal definition, we can say that the method used, so the method used only highlights a certain group for response. All right. So that's what sampling bias would be. So that means that I would choose to only ask kids that I know would say I'm a good teacher and not ask other kids because of the fact that I want them to represent it as, oh, I'm a good teacher. All right. But I don't care. All right. So, you either love me or you don't love me. I want the best for you, so you either love me or you don't. All right, so non-response, okay? So for non-response, guys, essentially that's actually one of the most straightforward ones, all right? People just don't respond, all right? So recipients do not, or they're reluctant to respond, all right? So you gave out a survey, all right, and they just didn't respond. So you can't get a viewpoint on what's being evaluated because of the fact that you're not getting any data back from them, all right? So that's what non-response bias would be, all right? So you just go with it because even though you didn't get any results, because you're saying if they didn't say anything, that means they're just agreeing, all right? It's what I would say when they're like, if you don't respond, it means it's a yes. All right. So that's what non-response bias would be. Okay. So how do the conclusions for observation studies differ from those in a randomized controlled experiment? So for observation, you're essentially seeing what's happening to in the experiment, or essentially what's taking place as the experiment is occurring. All right. So this talks more about association rather than causation. So rather than causation. All right. When for randomized controlled, all right, what you're doing is that you are randomly selecting people from your sample, all right, or from your population that you're assigning a certain treatment to, and seeing if that treatment made any difference, all right, in comparison to the person that did not get that treatment, all right. So, for example, if I'm stating that candy makes kids more hyped up, all right, or it makes them more energized, okay. So I would give everybody like a cup of water, and then in somebody's water, I'll put a little bit of sugar in it. All right, which sounds kind of weird, but I'm just saying that's kind of what I would use as an example, all right, and to see if that made a difference in how they behave that day, all right. So, but please do not put anything in anybody's water. All right, so so in this case, this talks more about causation because you're seeing if that the sugar you added made any difference, all right? So again, it talks more about causation rather than association, all right? So provide an example of cluster sampling, all right? So I'm going to use a different example than the one that we did in class, all right? So the example I'm going to use is, say, for example, we have, let me just use the same example because I don't have the time to figure out another one. So we have a district that wants to evaluate student study habits and our sample is interviewing students from 3 specific schools. All right. So essentially, what we're doing is that when you are doing a cluster sample, you're basically just trying to group things together so that you can find out if there's any similarities between those various groups that you cluster together. So for example, if I wanted to see the performance of students in algebra, right? So they want to see the performance of students in algebra across our district, okay? If I want to say, okay, let me see what Title I schools are like, I'll cluster all of the Title I schools in the school district of Lee County, and then I'll evaluate how did they perform on their algebra. Because hopefully they should have similar trends because they are a similar demographic, all right? And they should have similar results so that I can better know how to address those the results that I'm seeing, all right? So again, you're basically clustering them based on certain similarities, all right? And sometimes you can cluster them based on no similarities to see if there are any similarities that you'll see when you cluster them together. All right. So the next one we're going to do is binomial events. All right. It's one of my favorites. Okay. So it says we're trying to do mathematical models for probability associated with a binomial scenario. And I think there's going to be an application of geometric scenario. Okay. It's a binomial scenario, but we're going to use aspects of geometric PDF to try to solve one of these. So let's see if you figure out which one you're going to do that for. So it says the probability that a person prefers online classes over in-person classes is 0.65. So a person that prefer online, so prefer online, right, was 0.65. So then that means in-person, all right, was the opposite of this, or when you do 1 minus this amount, which is 0.35. Okay? So what I'm going to do is that I'm going to answer these questions. So it says calculate the probability that the first 4 students of 40 surveyed preferred online. All right. So when I'm doing this, guys, all I care about is that the first 4 prefer online. I don't care about nobody else. All right. Everybody else, they could prefer online. They could prefer no online. They could prefer to not even do the entire assignment. All right. It doesn't even matter. All I care is that the first 4 students preferred online. All right. I'm only caring about them. So I look for the probability that they will select online. And then I'm only looking for those 4 persons. Okay. So without replacement, I will just raise it to the 4th power. Okay. And then when I calculate this, I will get 0.1785. All right. So again, guys, just like that. So if 40 students are randomly selected, what is the probability that at least 15 of them prefer online classes? At least 15 means 15 or larger, all right? We are doing a binomial situation because you can either prefer online classes or you prefer in-person classes. So because we're doing a binomial situation, we're going to use binom. Because we're looking for 15 or more, because it says at least 15, so 15 or more up to 40, we're going to do CDF, a cumulative, all right? And then when you're doing binom CDF, the first area is the amount of trials you have. Because we're evaluating it for 40 students randomly, 40 is the amount of trials. Then we're looking for the person that prefer online, so we're going to look for the probability of online or success, which is 0.65. And then I need to evaluate 15 or more. But the thing about binom CDF is that it's calculating from 0 all the way to 15 as everybody picks their head up. All right? So, okay, so it does go from 0 all the way up to a certain number. That's how it does the cumulative frequency. It does from 0 onwards, okay? So it can't really do from 15 up to that certain number. So because of that, I'm going to calculate from 0 to 14, all right? And then I'm actually going to do it 1 minus that amount, all right? Because if I do 0 to 14 and I take it away from our entire data, it's going to show from 15 onwards, all right? So when you plug it in your calculator, guys, so this is what it would look like, all right? So for second function vars, go up, go to your binom CDF, all right? Your trials is 40, p-value is 0.65, and then you're looking up to 14, all right? Then we do 1 minus second function answer. So I got 0.99989. So this would be 0.99989. All right. So almost extremely likely that 15 or more persons prefer online. All right. So almost 100% likely. So it says, what's the probability that the first person selected that prefers in-person class was the 11th person? All right. So we have 11 people. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to represent persons that prefer online as a check mark and persons that prefer in-person as an X. So that means if the 11th person preferred was the first time they were in person, this was the first time you will have an X. All right, so this is the first in person. So that means all the other persons have to have been online. So online. All right. So because of that, guys, I would just go ahead and do something similar to a multiplicative frequency or something that you can utilize geometric PDF to find, right? But essentially, I'm going to multiply each of these probabilities, okay, and then multiply by the probability of in-person. So we have 10 of these, so this would be 0.65, because again, this represents online to the 10th power, multiplied by 0.35, all right, to the first power, because again, we had 10 people that were online, and then the 11th person was the only person that was in person, all right? So when I calculate this, guys, all right, 0.65 to the 4th power, multiplied by 0.35. So 0.6, not to the 4th power, I'm sorry, guys. So 0.65 to the 10th power, and then multiply by 0.35. All right, so this is what I would have gotten. All right, so you could have gotten this another way. So this would be 0.0047. You could have gotten this another way. All right, you could have gotten this another way, guys. We could have used geometric PDF. Okay, so if you press second function, because again, you're trying to find the specific area. So if you're using PDF, you're trying to find the 11th person specifically. So in 40 trials, if I'm looking for the 11th person, all right, so this is the probability of success, sorry. So for 0.35, because that's the probability that they'll be in person, where the 11th person is that in person, got the same probability, all right? So again, you could have done geometric PDF also. So for this one, guys, we're trying to do or evaluate any outliers in a stem and leaf plot, okay? So essentially, I need to do my 1.5 IQR rule, okay? So first thing I need to identify are my quartile 1, quartile 3, then IQR, then 1.5 times my IQR, then my upper bound or upper fence, okay? And then lower bound or lower fence, okay? So let's go and let's identify our quartile 1 and quartile 3. So you're going to have to put all of these into a list. So I actually already did this before. Some of you guys already knew this, okay? Where I did stat, edit, I already put my list in my list 1. So I press stat, 1 var statistics, all right? So then second function list 1, nothing in your frequency list. Calculate, so my quartile 1 was 41, quartile 3 was 74. IQR is Q3 minus Q1, which is 74 minus 41, which is 33. 1.5 IQR is 1.5 times 33, which is 49.5. All right. So the lower bound or the upper bound would be to the right of your quartile 3. So to the right of your quartile 3 means I'm adding to my quartile 3. All right. So I add my 1.5 IQR. So that would be 74 plus 49.5, which was 123.5. And then the lower bound is to the left of my quartile 1. So I do quartile 1 minus, because again, I'm going to the left of it. So to the left of it, you're getting more negative. So we subtract. So I do 41 minus the 49.5, and I get negative 8.5. Because we had no negative numbers in our stem and leaf plot, we had no lower outliers, right? And because we had no number that was bigger than 89, we had no upper outliers because we had no number that was bigger than, actually not 89, but 123.5, because our largest number was 89. So that's what I meant to say. So that means we have no outliers, okay? So next question. So the next question, we want to try to evaluate z-score. So we need to understand normal distribution and apply the z-score formula. All right. So the ages of students in a university follow a normal distribution. Researchers have collected data on the ages of a random sample of 800 students and found that the mean average age, or the mean age, is 22 years. So this was the mean. All right. So with a standard deviation of 4 years. Okay. So we have a normal distribution where the mean was 22, standard deviation was 4, all right? So it says, what's the z-score that corresponds to a student who is 26 years old, all right? That's an old student, all right? So to calculate this, guys, I would say z is equal to our x value minus our mean divided by standard deviation. That's how we calculate z-score by hand, all right? So the x value we're trying to find is the corresponding age, which was 26. Subtract the mean, which was 22, divided by 4, which is the standard deviation. 26 minus 22 is 4, and 4 divided by 4 is 1. Okay? So now we're going to find what's the probability of a student being younger than 20 years. So we have our normal distribution, where our mean is 22, standard deviation is 4, and we're looking for 20 or younger. So younger will be to the left of 20. All right? So when I'm doing this, guys, because I'm trying to find the area of underneath a certain region, all right, I'm going to use my norm. Because you're looking for the entire region, you're going to do CDF, all right? You're not looking for a specific actual number, all right? You're looking for the entire region. So in this case, you're going to have to do your lower bound. Your lower bound is not going to be to the furthest left as negative 1 E99. It's actually going to be 0. The reason why it's 0 is because you're talking about age, all right? So we're trying to see 20 or younger, so we're from 0 to 20. All right, so to 20, mean as 22, standard deviation as 4. All right, so again, something like that, you just put in your calculator, second function vars, norm CDF. All right, so 0, 20, 22, 4, bam. All right, so this gave me 0.3085. All right, so again, just like that. Okay, so what's the last one? So it says, what's the age, what age is associated with the 95th percentile? Because I'm trying to find the age that specific goes with this certain position, all right, I need to use inverse norm, all right? So when I'm applying inverse norm, I need to look for the percentile, which is 95, which is represented as 0.95, and then I evaluate my, I think the next aspect is my mean, and then my standard deviation, all right? So when I plug that in, I press second function vars, inverse norm, all right, so 0.95, then my mean of 22, standard deviation of 4. I'm looking at that left side, all right, so that would give me an age of 28, so that give me the age of 28.579, all right, that will round to be 29, all right, because again, it's age, so you can't be 0.5 of age, okay? So the next question. So the next question, we're trying to evaluate R and R squared and interpret what they are. So R represents the correlation coefficient, all right, while R squared represents the coefficient of determination. So based on our LSRS equation to the left, so I'm going to zoom out a little bit, all right, if R squared is 0.36, then what's the value of R? So to find R, all we're going to do is take the square root of R squared. So I take the square root of 0.36. And that will give me 0.6, but technically you get plus or minus 0.6. Because your R value can either be positive or negative. When you take the square root of a number, you always put that plus or minus sign in front of it, okay? So how do we know if the R value is positive or negative? Well, we need to take a look at our equation that we were given for a predicted value of Y, all right? And if your slope is positive, so again, if your slope is positive, that means R is greater than 0. In this case, our slope indeed was positive, so that means our R is greater than 0. So our R is actually positive 0.6, not plus or minus 0.6. So let's interpret what the Pearson's correlation coefficient in context means, right? So the Pearson's correlation coefficient is your R value, and our R value was 0.6, okay? So what does that really mean? Well, the first category is that you have to determine whether it's a weak, moderate, or strong correlation, all right? Because you're trying to figure out how correlated your values are to each other, okay? So in this case, 0.6 would be on a meter of moderate. At times, there's very weak and very strong, all right? But in this case, 0.6 would be somewhere in the middle, so moderate, okay? So we just found out that it was also positive, all right? Because the slope was positive. And then it's talking about this least squared regression line, okay? So that means it's a linear, all right? So it's a linear coefficient, all right? So it has a moderate positive linear relationship. And then it says in context, okay? So I mean to take into consideration what's happening here, all right? So it's a moderate positive linear relationship between number of hours studied and exam score percentage, all right? So between number, I'm just going to use a symbol, number of hours studied and exam score, all right, in percentage. Okay, so last one. So it says interpret the coefficient of determination. So the coefficient of determination is your R squared value, and our R squared value was 0.36, or can be represented as a percentage, 36%. All right. So the way that we could represent this or interpret this is that we could say 36% of variability associated between number of hours studied and exam score can be seen in percentage. All right, so there's a 36% of variability associated between the number of hours studied and the exam score. All right, so let's do the next one. So the next one, we're trying to utilize basic probability formulas. All right, so given the probability, this should be A, this should be B, is given. What's the probability of A union B if A and B are independent events? So you should remember the union formula, which is probability of A union B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, so probability of A was 0.4, probability of B is 0.5, probability of A and B, so this is something you should know off the top of your head. Probability of A and B is equal to the probability of A multiplied by the probability of B. Okay, so that's something you should know very well. Okay, so for here, I'll be doing 0.4 times 0.5. All right, so when you calculate all of that, you get 0.7. Okay, so the next one, so it says what is probability of A union B if A and B are mutually exclusive? All right, mutually exclusive essentially means that they do not impact each other. All right, so essentially, guys, when I'm trying to evaluate mutually exclusive, that means the intersection of them would be equal to 0. All right, so again, that means the intersection of them would be equal to 0 because they're mutually exclusive. All right, so that means they both can't occur at the same time. So in that case, that means that this formula, whenever it's mutually exclusive, can be represented as probability of A plus the probability of B. That's all. So probability of A was 0.4, probability of B is 0.5, so that'll give me 0.9. All right. So then the final thing, it says if probability of A and B is 0.2, then what's the probability of B given A? Are A and B dependent or independent? All right. So for this, guys, we're trying to calculate the probability of A, or rather B given A. So what we're going to do is that we're going to try to refresh our knowledge on what the given formula normally looks like. So the given formula is probability of A given B is normally represented as probability of A and B divided by the probability of B. All right. In this case, we're doing B given A. All right. However, what you should know is that the probability of A and B is the same as the probability of B and A. because that's what this will be represented as. This will be represented as probability of B and A divided by the second scenario, which is probability of A. So that's how I would represent it, all right? However, these two are the same because multiplication is commutative, so that means if you switch the order of them, you get the same result. 3 times 2 is 6, the same way 2 times 3 is still 6, all right? So essentially, I can just substitute the same value right here, 0.2 divided by 0.4, because that's what A was, 0.4, and I'll get 0.5, okay? So now I need to determine whether it's independent or dependent. For it to be independent, probability of A times probability of B needs to be equal to the given. So probability of B given A, all right? So essentially, if I multiply these, so technically this should be BA, all right? So if I multiply 0.4 times 0.5, 0.4 times 0.5, I get 0.2. Is 0.2 equal to the given, which is 0.5? No. So because they're not equal to each other, it's dependent, all right? So it's dependent, all right? So the last question, guys, last question. I'm going to go through it a little faster, all right? So we're trying to explore discrete random variables and tree diagram. A person commutes to work and encounters 4 possible traffic lights along their route. The probability of encountering a specific number of traffic lights are shown in the table below. So at 0 traffic lights, this was the probability. 1, 2, 3, 4, those are the probabilities. What's the probability that a person encounters at least 2? At least 2 means 2 or more. So all I have to do is just add these probabilities together. All right. So 0.4 plus 0.15 plus 0.05. All right. And that will give me the probability of 2 or more, which will be 0.6. All right. So I said, what's the probability that a person encounters no more than 1? So no more than 1 means 0 to 1. So I'll add these two together. So I'll do 0.1 plus 0.3. All right, and this will be 0.4. So the next thing we're going to do, what's the expected number of traffic lights encountered during the commute? So all we're going to do is multiply each of these probabilities by the occurrence, all right? So multiply each of those probabilities by the occurrence, or you can put in your calculator and let your calculator calculate it for you, all right? But again, this is another method you guys can utilize that uses more by hand, all right? So 4 and 0.05, okay? So again, you get the same thing as if you made 2 lists. So if you had made 2 lists with those same things, 0 to 4, and then 0.1 to 0.05, and run your stat output. So run your stat, 1 var statistic, where this will be your list, this will be your list frequency, because that's a probability. You'll get the same 1.5, which is the same thing as if you multiply all of these and add them up, all right? So if I multiply all of these, 0 times 0.1 plus 1 times 0.3 plus 2 times 0.4 plus 3 times 0.15 plus 4 times 0.05, I'll get the same 1.75. So again, guys, just like that.